Hi, sir. This is T. Kushri from ITA section. My topic for Tech Talk in physics is delta star transformation approach for reliability evaluation. So, my topic is about how to transfer a given circuit from delta to star. As we can see in the picture, we are going to derive the formulas to convert a delta circuit into a star circuit. So, delta star transformations. The replacement of delta or mesh by equivalent star connection is known as delta star transformation. The two connections are equivalent or identical to each other if the impedance is measured between any pair of lines. That means the value of impedance will be the same if it is measured between any pair of lines, irrespective of whether the delta connected between the lines or its equivalent star is connected between that lines. So here we are taking a delta circuit which is named as A, B, C with resistors R1, R2 and R3. So this delta circuit is be converted to star circuit with the same notations A, B, C, and resistors are RA, RB, RC. So let us derive the formulas to convert a delta circuit into a star circuit. So let us go through the derivation. Consider a delta system that's three corner points are A, B and C as shown in the figure. Electrical resistance of the branch between points A, B, B, C, C, A are R1, R2 and R3 respectively. The resistance between the points A and B will be, so since R1 is parallel to R2 plus R3. So resistance between the points A and B is R1 into R2 plus R1 into R3 by R1 plus R2 plus R3. Now one star system is connected to these points A, B and C as shown in the figure. Three arms RA, RB, RC of the star system are connected with A, B and C respectively. Now if we measure the resistance value between the points A and B, we'll get R of AB is equal to RA plus RB. Since the two systems are identical, resistance measured between terminals A and B in both systems must be equal. Therefore, RA plus RB is equal to R1 into R2 plus R1 into R3 by R1 plus R2 plus R3. So this will be our first equation. Similarly, resistance between points B and C being equal in the two systems, so RB plus RC is equal to R2 into R3 plus R2 into R1 by R1 plus R2 plus R3. This is equation number 2. And resistance between point C and A being equal in the two systems will get RC plus RA is equal to R3 into R1 plus R3 into R2 by R1 plus R2 plus R3. So this will be our equation 3. So here in this slide we got equation 1, equation 2, equation 3. Now adding equations 1, 2 and 3 from the previous slide, we get 2 times of RA plus RB plus RC is equal to 2 times of R1 R2 plus R2 R3 plus R3 R4 by R1 plus R2 plus R3. Then here 2 gets cancelled on both the sides. Then we'll get the equation as RA plus RB plus RC is equal to R1 R2 plus R2 R3 plus R3 R1 by R1 plus R2 plus R3. So this will be our fourth equation. Now subtracting equations 1, 2 and 3 from equation 4, we get the following equations. So first we are going to subtract equation 1 from equation 4. If we subtract, we'll get RA is equal to R1 R3 by R1 plus R2 plus R3. This will be our equation 5. Next we are going to subtract equation 2 from equation 4. Then we'll get RB is equal to R1 R2 by R1 plus R2 plus R3. This will be our equation 6. Next, if we subtract equation 3 from equation 4, we are getting RC. RC is equal to R2 R3 by R1 plus R2 plus R3. This will be our equation 7. The relation of delta star transformation can be expressed as follows. The equivalent star resistance connected to a given terminal is equal to the product of the two delta resistance connected to the same terminal divided by the sum of the delta connected resistance. So from the previous slide, equation 5, 6 and 7, these are the equations or these are the formulas to convert a delta circuit to a star circuit. If the delta connected system has some resistance R at its three sides, then its equivalent star resistance R will be R is equal to R into R by R plus R, that is equal to R by 3. So finally, what are the delta star transformation equations? If we consider in alphabets, it is P is equal to AB by A plus B plus C, Q is equal to AC by A plus B plus C, R is equal to BC by A plus B plus C. If the three resistors in the delta network are equal in value, then the resultant resistors in the equivalent star network will be equal to 1/3 the value of the delta resistors. This gives each resistive branch in the star network a value of R star is equal to 1 by 3 into R delta, which is same as saying R delta by 3. So delta star conversion, we'll see one example. So convert the following delta resistivity network into an equivalent star resistivity network. So here resistors values are given as R1 is given as 20 ohms, R2 is given as 30 ohms and R3 is given as 80 ohms. So to get the resistors QPR, we already have the formulas as AC by A plus B plus C is the formula for getting Q, and for P it is AB by A plus B plus C, and for R it is BC by A plus B plus C. So if you substitute R1, R2, R3, that is A, B, C values in these formulas, you will get Q, P and R as shown. So we'll see another example for delta star conversion. So as you can see in the picture, we have to convert the delta circuit or delta network to a star network. Here we are given three resistors. R1 is 10 ohm, R2 is 60 ohm, R3 is 30 ohm. So given resistance of delta networks as R1 is 10 ohm, R2 is 60 ohm and R3 is 30 ohm, we know that we can use formulas to get it converted to star. So we know the following relations of the resistances of star network in terms of a resistance of delta network. RA is R1 R2 by R1 plus R2 plus R3. RB is R2 R3 by R1 plus R2 plus R3, and RC is R3 R1 by R1 plus R2 plus R3. So now we'll substitute the values of R1, R2 and R3 in the above equations. So RA is equal to 10 into 60 by 10 plus 60 plus 30, that is equal to 6 ohms. RB is equal to 60 into 30 by 10 plus 60 plus 30, that is equal to 18 ohms. And RC is equal to 30 into 10 by 10 plus 60 plus 30, that is equal to 3 ohm. So we got the resistances of a star network as Ra is equal to 6 ohm, Rb is equal to 18 ohm, and Rc is equal to 3 ohm, which are equivalent to the resistance of the given delta network. The methods for reliability evaluation of a complex system using delta star transformations have been developed by several authors. They give approximate results because the basis on which the transformation is derived is not correct. These transformations can be carried out under certain conditions. So let us first see these notations. SI is sets of branches, that is excluding the branches forming the delta connected to node I. R of ij, reliability of the component connected between nodes I and j. Q of ij is probability open circuit failure of the component connected between nodes I and j. Q of ij is probability of short circuit failure of the component connected between nodes I and j. R is system reliability. Conditions for transformation. In delta star transformation, three independent conditions are to be imposed as there are three elements to be determined. So first, let us assume things. So first thing is the component states are S independent. The branches of one set out of sets S1, S2, S3 have flow into the corresponding nodes. And the next is the reliability before and after the transformation is the same. Between node 1 and nodes 2 and 3, when all three sets are present, between node 1 and 2 when S3 is null set, and between node 1 and node 3 when S2 is a null set. So reference 1 to 3 do not satisfy the condition 3a. Also the expression derived for conversion in 1 to 3 apply only when condition 2 is satisfied. If there is no restriction on the flow outside the delta, then 6 conditions are to be satisfied and hence transformation will not be possible in general. And the next is state device network. Consider for example 3 components. Each component has 2 states. Example, operating and failure of a system with reliabilities R13, R12 and R32 connected to form the delta configuration as shown. This configuration can be transformed into star equivalent with reliabilities R10, R20 and R30. Applying S independent even probability loss to series and parallel components results in equation 1 minus 3. So R10 and R10 into R20 and R10 into R30 formulas are derived in this slide. So solving 1 and 3 from R10, R20, R30 results in the relations for delta star transformations are R10 is equal to O1 O2 by O3, R20 is equal to O3 by O2, R30 is equal to O3 by O1. And O1 is R12 plus R13 into R32 minus R12, R32, R13. And O2 is R13 plus R12, R32 minus R13, R32 and R33. And O3 is R12, R32, R plus R12, R13 plus R32, R13 minus 2 times of R12, R32 and R13. And the next one is state device network. The delta to star equivalent of a network consisting of 3 state devices, example, operating, short circuit failure, open circuit failure, can be obtained in the same manner as 2 state component case. The expression of a leg equivalence for the open mode failure cases are Q of 10 is 1 minus x1 y1 by z1, Q of 20 is 1 minus z1 by x1, Q of 30 is 1 minus z1 by y1. x1 is 1 minus q of 12 into q of 13 minus q of 23 into q of 13 plus q of 12 q into q of 13 into q of 23. In the similar way, you will have values for y1 and z1, and using these formulas you can convert a delta network into a star equivalent network. Similarly, the expressions for the leg equivalents for the short circuit failure cases are as follows. So for the short circuit failures, you will have the expressions as derived below, that is Q10, Q20, Q30, XZ, YZ and ZZ expressions are derived. Using these expressions, we can convert a delta network into a star network. So we are considering an example. Consider the bridge network shown. Use equation 4 minus equation 6, then the equivalent star configuration is derived. So if you subtract equation 4 and equation 6, the following R10 and R20 are derived, and these are star configurations. So evaluating reliability of this bridge structure with the event space method yields the same expression for system reliability. So I hope you understood this topic, and the conclusion is that to minimize the complication of a circuit, we use the delta star transformation so that the circuit will be solved in an easy way. So I hope you understood this, and thank you so much.